Hello, this is the next video in a playlist that I'm calling Complex Variables, which is going to comprise lots and lots of different topics in complex analysis and variables. But this part of the playlist is complex numbers. So let's jump to today's topic, which is the modulus of a complex number. Now, the modulus, also called the absolute value of a complex number, and so is defined as the absolute value of z is the a squared plus b squared. So it's the square root of the square of the real component and the imaginary component. Now this is analogous to the absolute value in for a real number, which calculates the distance from 0 to that number. And so this is the distance from the origin to this complex number. Now I have an illustration. I'm not going to review the R code, but I want to display it in case anyone's interested. Here it is. So we have a complex number z, and we want to find the distance from it to the origin. And we can create this right triangle. So this distance is 3, and this is 4. So the Pythagorean theorem tells us that this distance is 5. So the modulus of z, which is 3 plus 4i, is 5. Now, if this angle is theta, then we can create, instead of calling this distance y, we can call it 5 sine of theta. And this distance, instead of calling it 3 or x, we can call it 5 times the cosine of theta. And that's really the topic of the next video. So some properties of modulus. Let's let z1 and z2 be complex numbers. We want to prove that the modulus of the product of complex numbers is equal to the product of the moduluses. Or is it moduli? Help me with that in the comments. So let's look at that. So the modulus of the product is this, and then we've covered the multiplication of complex numbers in a previous video, and we get this. So this is the real component, and this is the imaginary component. Remember, we're taking the modulus of it, which means the square root of the square of the real component plus the square of the imaginary component. When we multiply these out, we get some cancelizations, and then we can refactor it into this. And since these are all real numbers, and this is positive added to a positive, this number is positive, and this number is positive, so we can break it up into this. And I illustrate that because in the complex world, you always can't break up the square root like this in this fashion. Actually, that reminds me of a video where we prove that 1 is equal to -1 using complex numbers, and it's essentially this trick, but it's violated because the two numbers are not positive. And if anyone's interested in that, I'd be glad to make a video on that and illustrate that property more. But then this is the product of the two modulus of the complex numbers. Here we want to show that the modulus of the division of two complex numbers is equal to the division of the moduluses of two complex numbers. And that's assuming that z is not the origin. Remember, z equals 0. That means it's 0 plus 0i. So it's the origin. And let's go through that. So that the division is this of the two complex numbers, and we've covered division of complex numbers in a previous video in this playlist, and it boils down to this. So this is the real component, and this is the imaginary component. And we're taking finding the modulus of this complex number, which means we're squaring this component and squaring that component. Let's combine these into one fraction, which is this. And the numerator, you get some cancelizations, but it ends up being this. And then this can be factored. The numerator can be factored into this, but the c squared plus d squared cancels with one of these, and we get this. And now note that since the numerator is a positive real number, and this is a positive real number, you can break it up into the square, the square root of the numerator divided by the square root of the denominator, which is just the modulus of these two complex numbers. Now let's prove the triangle inequality holds for complex numbers, and that can be thought of as this is the hypotenuse is always less the length of the hypotenuse is always less than the sum of the lengths of the legs. So let's do it. This inequality, if this holds, then this holds, right? The modulus of the complex numbers, and then the sum of the moduluses. Now, really, this should be a question mark above this inequality because we don't know it's true yet. But if this is true, then by definition, it's what it means. So if we square both sides, we get this piece here. Now, when we multiply out these quadratics, we get some cancelizations, right? The a squared, b squared, c squared, they all cancel, and we're left with this piece right here. Now, the 2 cancels with a 2 over here. Well, if we square each side of this inequality, we get this. And when we multiply this right side out, we get cancelizations over here, and it's left with this. If we subtract this to the right side, from both sides, then that is this squared component. But since these are real numbers and then we're squaring it, it's always greater than or equal to 0. So this is true. And then you can backtrack. This is true, 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 true. So then this must be true. And then we've proved the triangle inequality in complex numbers. Now this can be extended to any number of complex numbers. I'll illustrate it with 3, but really it could be m complex numbers. We want to prove this inequality. So we bring this down. Now note that if we think of as z2 plus z3 as a complex number, then the previous property tells us that it's less than or equal to this piece. But then we apply it again to these 2 complex numbers, and we get this, right? And that's what we wanted to show. And that can easily be extended to m real numbers. Let's prove this inequality. Okay, so to prove it, we know the modulus of z1 is equal to this, right? We're adding and subtracting the same quantity, so it's adding a well-chosen 0. But then the previous property says that this complex number plus this is less than or equal to this quantity. And if we subtract the modulus of z2 to the other side, then the result follows. And now we have a minus here, but really it can be a plus and we get the same thing. And the way to prove it is you plug in a minus z2 here, and then it immediately falls out, and you can show it's true. Now this next property I actually find quite fascinating because it's not obvious to me. So we want to show that the real number of a complex number greater than 0. So that means the right half of the complex plane is equal to this inequality. And so we let z be this complex number. So we look at this inequality, and then we, by definition, the modulus of z minus 1 is this, and the modulus of z plus 1 is this. We square both sides, subtract b squared from each side, we get this. Multiply this quadratic out, we get this. A squareds cancel, 1's cancel, minus 2a plus 2a, take it over, divide by 4, we get a is greater than 0, which is exactly the real component greater than 0. And that's what we wanted to show. And then also you can back trace it and show that it is equivalent. Okay, well that's all I have for this video. The next video is on polar form of a complex number. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.